Good afternoon, and hello again to a few of you I see who are familiar from a talk I did earlier. Graph is something I've been working with for nearly 15 years now. And most of that time, frankly, it's been a dreadful struggle. Back in 2000, when we first started to impose graph structures on top of relational technology, a few 100,000 facts, the triples that make up a graph, was an awful lot of data, but it was almost useless in terms of having a practical use. And in fact, my colleagues at IBM were extremely scornful and said, "You'll never make it scale." And they were almost right. I left IBM in 2007 to found Cambridge Semantics, and a good chunk of the 11 years that have passed has been attempting to scale graph. I'm pleased to say that, well, first of all, who here has worked with graph databases in the past or recently? In the past and recently? Not too many. Okay. Well, I suspect that's going to start to change. I don't know if I'm the road to Damascus, but we're starting to see that this technology is really started as an inferior technology. It will soon start to supersede many of the use cases that we have been relying on, other often relational and other tabular-oriented technologies. This technology will start to supersede that. And one of the main reasons for that is because we have finally achieved sufficient scale to make this practical for most types of use cases. So I'm going to talk a little bit about some of this and the landscape, and then the second talk will get into more of the nuts and bolts of the elements of the technology, and included some demos. So it hopefully will be an interesting hour or so. You can go to Wikipedia and look at the entry graph database, and there's sort of a history of them listed up there, but there's a bunch of new ones, and that's very exciting. And there's a bunch of new ones of companies that are pretty serious. One of the companies that you may have heard of is a company called Marklogic, who converted to graph and RDF a few years ago, and have really put a lot of effort and investment into that, and they've got that working pretty well. Another big and important one is, and I'm going to be making the case that 2018 is the year of the graph, and it is. If it isn't this year, as well as next year and thereafter, I suspect we're looking at this being the decade of the graph, starting probably last year. One of the early announcements last year that I noticed that is sort of a bellwether for me was Thomson Reuters, who sell data, they sell massive amounts of data, announced that they would make their data available as a graph, so you could actually buy it in all of its glory and complexity and interconnectedness from them. So that happened late last year, and then was not too long after followed by an announcement by Amazon, who've decided that there's enough there for graph that they would actually put together an offering, which I happen to know they'd probably been working on for a couple of years prior. So these are sort of big events for people who've cared about graph, because they start to show us that the mainstream is taking notice, and both Thomson Reuters and Amazon are certainly by anyone's definition the mainstream. And I'm going to cover a few of the reasons why I think graph is starting to get very interesting. I'm not going to particularly cover the very technical aspects of it, except to say that really there's not much you can't do with graph that you can only do with SQL. In other words, the graph technologies now are superseding what the relational technologies are capable of. And one of my colleagues, who's a dyed-in-the-wool analytics guy, a gentleman by the name of Barry Zane, who some people may know, he's one of the gods of analytics in terms of warehousing. He built the original Netezza systems and Paraxel, which is also the Redshift system. So somebody knows a lot about SQL. When he gives a talk similar to this, he actually goes and shows you SQL queries and Sparkle, which is one of the graph languages we support. He shows the difference. And what he shows is how everything you can do in SQL is possible in Sparkle, but then there are these extra queries you can run. And the queries are around the relationships, because graph is all about storing and understanding and retrieving relationships. And unlike a SQL system where you have to kind of poll, are these things related like this, or are they related like that, or are they related like this other thing? We have to kind of exhaustively know all the ways things might be related and format a SQL query to ask that. With graph, you can say, how are these things related, and get back a whole list of how things are related. And that is a very important difference. So that is from a technical point of view what is changed, but really it's something deeper than that. Graph allows us to structure data far more naturally. If you've grown up with relational technology, you may not realize it, but most of the world doesn't fit into tables with foreign keys that interrelate with each other. It's an unnatural act unless you're a double entry bookkeeping system. But that is what we've had to use for all these 30, 40 years, because that was efficient. And it was all about the efficiency and getting throughput and so on. But we've turned the corner in recent years in that we now have so much capacity in terms of our compute, multi-core systems, our networks that are very high bandwidth, this massive amount of RAM and even more promise of interesting RAM technologies and memory technologies to come, that finally we're now able to arrange data for the benefit of the consumer of the data and worry less about the efficiency of the processing, and basically having to skew our whole world around making processing efficient. So this is an interesting development, and now finally we're actually seeing software products that are bearing this out. So one of the reasons why is because graph database offerings are beginning to show maturity. You're actually getting production use cases of serious, well-established customers doing serious work with different kinds of graph bases. And different kinds is an interesting point of view, because we're actually starting to see segmentation in the technology. Just like we saw in the relational world, we're now starting to see OLTP style graphs as well as OLAP style graphs. And for those who don't know the difference, one is really about transaction processing and the other is about analytics processing. So and there's examples of each of these. So in the case of the OLTP, we're doing single record fetches generally. We're looking close in and we're doing reads and writes pretty rapidly. We're doing transactions. We care about ACID, those kind of things. And these are examples of the sort of relational versions of OLTP as well as some of the graph versions. Now, it's a little confusing. Cambridge Semantics is in both the OLAP and the OLTP. That's because our products both have persistence metadata stores, which are transactional, but we also have an OLAP graph, which are obviously doing much more complex, join, aggregation style, warehouse style queries. And those you could compare with systems like Teradata and Netezza and Redshift and so on. So finally, we're seeing on both sides of this divide, we're seeing credible products that are delivering real solutions and they actually stand up and work at scales that are meaningful. And that means that we're able to, for the first time, really achieve the promise of graph. And all of the things that we wanted to do, that, as Barry would say, if we had graph back in 19, and he probably doesn't say the year, we would have used that instead of relational technology. So you had a question there.
I don't see Marklogic, just curious.
Because I forgot to put it on the
Where would that
on the left.
only on the left?
I think so. I'm not. Listen, all the vendors may argue, but my view is the relative speed of the aggregate queries and things. There's really almost 2 orders of magnitude difference in performance. I've never benchmarked their code. I'm just guessing where they're going to fall. So if they're not there, I'm not really particularly making a statement about them. Sorry. So I've never benchmarked. I don't know, but I'm guessing they'll fall more to the left. One of the interesting observations is that in-memory systems will start to push somewhere between the two. And I think that'll be true of relational as well, but certainly going to be true of graph. And in-memory is part of the reason how we are managing to solve the scale problem for the aggregate query. It's partly all that horsepower coming online in terms of hardware and riding a curve of the sort of arc of underlying technology improvements. And then it's also the right people who have the right experience applying themselves to the problem for enough years to actually get that software in place. So this is a bit of the landscape. It's not, as you pointed out, it's not exhaustive. I actually had to blot out Teradata because someone who made this slide had Teradata on the left, which is obviously wrong. So here's and I guess these slides will be available so you can look at this in more detail, but here's a notion of the kinds of things that these different databases are good at. And it sort of follows the same lines as in the relational world. And so the same things you already know about the difference between OLAP and OLTP, that applies here. And there's a huge, huge difference in performance. We really have struggled to try and we used the OLTP stuff matured much quicker. Unfortunately, the use case that we were most interested in was data integration and harmonization. And we were really stymied because the focus and the performance is more on the OLTP side rather than the OLAP side. Yes?
What does this say?
What this says is the types of queries that you can expect. So let's...
What do you mean expect?
Well, when I do an OLTP query, I tend to be reading and writing very fast and doing transactions, and I care about ACID, and I care about record-oriented accesses. When I'm doing OLAP, I'm really worrying about aggregations. I'm asking, instead of about Steve, a single record, I'm asking about an entire population of what did they do and what's...
But what does it mean that you put them in one column or the other?
The top column tells you the names of databases.
Are you saying that the things on the right-hand column are things that are done better in osograph and tigrograph?
Yes. Sorry that wasn't clearer, but yeah, that's exactly what it's saying. Okay. Second, graph is being used beyond the classical graph problem. So graph has been a niche thing for forever and ever. And people were highly tuning their applications, and they were often taking a walk on the wild side when they decided to get into graph, and many failed and were burned by graph failing for often scale reasons, but other reasons as well, including immaturity. So you ended up doing pretty exotic stuff with it only. That has started to change too. So a classical problem would be understanding the relationships between two entities in the graph and trying to understand all the ways people are connected. And I mentioned earlier that graph query languages are very good for extracting those kind of relationships. But where we're finding traction in our business is building massive scale knowledge graphs and doing I used this slide a bit earlier, but doing things that allow our customers to accelerate entire pipelines that involve hundreds of applications and data movement and transfer between hundreds of applications. In this case, it's the life science business is attempting to bring drugs into the world. Currently, it's 10 to 12 years. They want to halve that. They want to decrease the amount of time it takes them to do that. How do they do that when they've got hundreds of applications, hundreds of data systems across that sort of life cycle? How do you look at decreasing that? And the answer is to use graph technology to make the handoffs of data much more natural. And the fidelity at which the data data forms that graph use tends to be much richer and more descriptive and easier to move around, particularly if you use standards. There's no ETL required. One of the most exciting things about the Neptune announcement is that they support RDF and Sparkle, which means that the same, and people will start to write applications as that database goes live, the same data that's in there can be taken directly into the Anzo graph system and used without any ETL. We literally just need to move the data across, and there's no transformations required, and we will be able to use that data directly. That's a pretty big change when you can imagine more and more applications, more and more places where data is created will use these standards to generate data, and everybody else who wants to do analytics will be able to use that information without any changes directly. So it's a sea change, and that's the sort of thing that some of our customers are seeing in terms of how they can build a knowledge graph that spans their entire business and allows the movement of data horizontally across the business. Instead of concentrating and improving each little silo and polishing that silo, they can now think about data sweeping across the business, which can help to accelerate and reduce the amount of time it takes to actually get their business moving quicker. So examples now, we're moving away from how do these two things get related. We're looking at how to harmonize dozens, hundreds of data sources and create a continuum of those in these knowledge graphs and be able to tie together. In this case, we're trying to represent a number of different sources and show how those tie together. They come from different places, but there's but a graph is the structure that's capable of tying them all together and holding that set of connections. In the case of, here we have what looks like a regular dashboard with a pop-up, which is actually the model over the top of it. What we're seeing is a dashboard that's not anymore built just on tabular extractions, but it's built through connections from the model all over the graph. So you're actually seeing denormalizations into BI tools and discovery tools from all over the graph into what looked like regular sort of BI dashboards. But the mechanism for getting this data and bringing it in is much more sophisticated, and it means that far less work is necessary to actually build reporting across these vast knowledge graphs that we're putting together. Another example would be using an existing tool, Tableau, surfacing a graph inside that of what data might be available, allowing a user to select a couple of classes and having those materialize as tables. Same thing with self-service analytics. The models we have drive query generators that allow end users to much more quickly create their own denormalizations of data, and the underlying graph queries, the complex queries underneath, are ones that can get generated automatically because of these models. The information fabric is this notion of creating this knowledge graph and creating the semantic models over the top that describe the data in the knowledge graph, and providing the sort of access of protocols, things like REST protocols, like OData, for example, which in turn can look like JDBC and ODBC, as well as other protocols that provide a common set of access. So providing a layer of meaning, business meaning, using semantic models, which are modeled as graph, and also providing a common way of accessing this data that gateways into current tools. Graphs, this is a model, I've showed it earlier, but this is actually a model, it's not the instance data. So each one of those circles represents an entity in a bigger knowledge graph, in this case something to do with drug discovery, I'm not sure about the domain. The different colors represent different data sources that are coming into this harmonization of data. So you can see the models can get extremely rich and detailed. These are the sort of companies that are leading the charge in terms of implementing the fabric using knowledge graph technology. Let's just zip on here. Third, I'm going to get to the transformations later because it's kind of, I think, where the future of this is going. And I talked about a semantic layer in my earlier talk, but the idea is to use these knowledge graphs to create a single layer of meaning over the top where everything's tied together, and to make combinations of data that have been extracted and abstracted and extractable from all these different sources without worrying about the format or the underlying naming and so on, and making all that appear to a user as something very understandable. Anzo Graph is a very powerful, massively parallel system, so it's like a Teradata in terms of its parallel nature. You can scale it linearly. This is our OLAP system, so it looks a bit like a Redshift or a Teradata or that ilk, except that it's graph oriented. We loaded a trillion triples into it a year ago, 200 node cluster on Google. We did it in, I think, about 2 hours. The previous record was an Oracle Exadata system, which was 9 days. The load time was half an hour. So we managed to load a 200 node cluster in half an hour. That's change coming. I'm not going to go into why it's so fast. If anyone's interested, can come and talk to us about it at the booth. So what lies ahead? I think that one of the killer applications for graph that we're really going to see accelerate its adoption is feature engineering for AI. So one of the problems of ML is arranging your data in these very wide tables where each column in the table is some sort of aggregation that exposes some element of the underlying graph of connected data that you're going to want to train a model on. And the automatic query generation coupled with the graph is a way of corralling complex domains of data and many different sources into something that is digestible by neural nets. I think this is going to be the harmonization of data was certainly one of the drivers for the last few years. I think this is the next, it's going to pick up the yoke. And this is what I really meant about complex data transformations being really good, because if you're building these sort of denormalizations that are a couple of hundred columns wide, and each column represents a subquery of some complexity, that's a very tough thing to do manually. It's a bottleneck right now. And I am out of time. But if there are any questions, let's see. We've got half an hour left, which is about, I think, right. If there are any questions, very briefly, one or two. Please go ahead.
You said at the beginning that it's recently become scalable.
Yeah.
How and why?
A combination of the software has become available, and because we're now, I think we have easy access to these massive on-demand compute farms, the homogeneous compute, and people have optimized software around that. And the other reason is pretty simple. The guys who were building the really big scalable systems before got a little interested 5-6 years ago, and it's taken them that long to actually write the code again, but around the graph. So I think at least that's true for OLAP. For OLTP, it's followed a progression over probably the last 15 years of people increasing. So people like Neo have really blazed the way with single node replicated systems. The Neptune guys also similar. So they've blazed a long trail around their OLTP, and that worked quite well to the extent that you could do things around indices and get very fast reads on local records. But the OLAP people had to do the full shuffling of data and these sort of huge distributed joins and make that work at scale on commodity clusters. And it's taken 6 years. Okay.